Hello, calculus students. This video is for chapter 3.3, Differentiation Rule. What's differentiation rule? Basically, we say when we find derivative, we actually, by definition, we have to go through limits. But if we have done some limit and we see that, oh, every time we do it, we get the same answer, we can write out the rule, and then whenever we want to do a derivative function that's similar to what we have seen before, then we would just use the differentiation rule. So what happened is these are not new rules to find derivative, but it's actually a result of doing limits. We just borrow the result or we look at the pattern that it works. So the first one is the constant rule, meaning if I have a function, so the one in the middle is the function that you are interested in finding the derivative. So if my original function is f of x, about here, f of x is c, it's a constant function, and I want to find f prime of x. So of course you have to do limit, right? So the correct way is to find anytime you have you have a function that you want to find this derivative, you have to find limit. The limit of x approach 0 is always x approach 0. F of x plus h, you still remember this formula, minus f of x. There's no exception, just one formula. Every time you find f prime of x, you do that. Except in this case of a constant, your f of x plus h and your f of x are both c. So what you have is a limit h approach 0, c minus c over h is just equal to 0. So even before you do direct substitution, you don't have to. This limit is a constant 0. So we would have 0 no matter what c is. So next time when we're dealing with a constant function, we'll say, well, let's not write this limit. Let's just say that d dx of c is equal to 0. d dx is a differentiation rule that let us write the derivative function right away. And this, in the same token, we have another rule. This rule is called power rule. What happens is if your function is x to the certain power n can be an integer or a rational number, meaning a fraction, then you can do d dx x to the n is n x to the n minus 1. And I have done a demonstration of this in class when we have f of x is equal to x squared. I did it in class for every class that I teach. Our f prime of x is 2x. And when my f of x is x to the cube, there's some kind of pattern, right? We actually do the limit. We actually use the limit to show that it is 3x squared. And then we even do f of x equal to x to the 4. Actually multiply f of x plus x fourth time out. My f prime of x is 4 x to the third. So it matches the pattern, and actually in the book, if you look at the calculus book, they actually do x to the n using binomial theorem to prove that the limit is n x to the n minus 1. So this is a rule that always applies. So whenever we see x to the n, we don't go to do limit anymore. We just use the rule because it has been proven. It is the result of a limit. The next one is sum and difference. If you have two function and you want to if your function is a sum of or difference of two different functions, you can just do them individually. Now mind you, this is only for sum and difference, not for product or quotient. If you multiply two functions, their derivative is not the products of it or the quotient of it. We'll talk about those at the second part of 3.3. And then if you multiply your function by a constant multiple, then you would just move the constant multiple out and just do the derivative of the function. So we use d dx as kind of like a notation that say we are taking derivative of it by some rule. Okay, it actually just means that whatever that has been calculated for limit of this function, we'll use it. For example, the first example is we have f of x equal to 5x cubed plus 2x plus x, and we want to find f prime of x. Notice that these are all x to the something, and a constant. And we have some constant multiple, so we would just do the d dx to do it. So what we do usually is notice if they are written in x to the n. This is x to the 1. If you want to, you write it nicer. So we would say then f prime of x would be not the limit, but d dx 5x cubed plus 2x plus 8. And then we just do them individually. For the first one, 5 is a constant multiple, so we write 5. So x to the cube become, by the power rule, 3x squared, because 3 minus 1 is square, plus 2 times 1, because x to the 1 is here, and then x to the 0 is just 1. And then constant is 0, so you just leave it behind. So it becomes 15x squared plus 2. That is the derivative function of the original one. Much faster than doing limit, right? So because someone has done the limit already, you just make use of the results. Now let's do f of x have some fraction, and also the power is a negative and a rational number. So what do? Again, we write it like this. F prime of x is d dx. So the first step is to just write f prime. What do? We do the derivative of x to the negative 1 minus 4x to the 1/2. This step also want us to remind ourselves, oh, these are written in x to the n format. Then we would do it here. We would say this is a constant multiple, so we just write it. And then what do we have in the power? It's -1, just multiply -1, and then x to be -1 minus 1 is -2, minus 4 times. What is the power? The power is 1/2, and then x 1/2 minus 1 is -1/2. So we multiply this constant multiple together, -5/4, x to the -2, and 4 times 1/2 is 2, minus 2, x to the -1/2. Usually, we do not write negative exponent in the answer, so we move it back, or if it is a 1/2, we write it back into radical. So we'll have -5 for x squared, right? -2 means it's a reciprocal, so go in the denominator. Then -2 square root x. -1/2 means it is a reciprocal, and 1/2 is a radical. So that's how you find the derivative using the basic differentiation rule. So the third example involves some radical. So now the radical is not a power form, and this is 1 over x cubed is not in power form. So the first thing we do is we would write f prime of x by rewriting each one so that they are in power form first. 1 over x cubed, I will write it as x to the -3, minus x half, I can write it as x 1/2. X root is 1/2, plus x cube root of x would be x 1/3. So write it so that they're all in that form. So we're not doing the derivative. The differentiation rule is still waiting outside. This is a rewriting. Now we're ready to apply the power rule. So the power is -3, so we would say -3 x to the -4. Then minus, the power is 1/2. And when we have 1/2 minus 1 is -1/2. We did that in the last one. And then what about 1/3? We just do 1/3, and it will be 1/3 minus 1 is -2/3. Okay, so now the last step is to change them back into positive exponent, having the proper reciprocal and radical taken care of. 1/2, -1/2 is the reciprocal of the square root in the denominator. -2/3 is also the reciprocal of 2/3. So you can either write 2/3 or you can say x squared cube root. Both of them are okay. Next one is, this one has more complex power. So we will say I need to do f prime of t. So notice the variable is not x but t, but you can still do it. But instead of writing d dx, you write d dt. Okay, dt. That means t is what you are doing the derivative on. The first one is okay, so this is just a rewriting. So we just copy it over. But the second one, you have to do 3 t to the negative 1 so that it's in proper form, minus 2 t to the negative 1/2 because it wasn't a denominator and it's a root, it's a square root. So these are all in power form and we are ready to do. So the first is negative 5 times 4. T to the 4 minus 1 is 3. Minus 3 times negative 1. T to the negative 2, right? Negative 1 minus 2. And then this is negative 2 times negative 1/2. T to the negative 1/2 minus 1 is negative 3 over 2, negative 1.5. Now it is rewriting. So this is negative 20 t cubed add 3, but I have a t negative 2, so t 3 over t squared. What about t negative 2 and negative 1/2? They cancel as 1. So plus t, oh no, this is 1 over, because it's negative, t to the 3 over 2. Now 3 over 2 is not the same as 2 over 3. 3 over 2 can be written as, so this part you can rewrite it as 1 over t times square root t, because this is 1/2 and this is 1. 3 over 2 means 1.5. So that's the final answer.